Hello everyone, welcome to this one-shot review of Unit 5, Analytical Application of Differentiation. This is for both AP Calculus AB as well as BC. In this video, we will be diving deep into the critical aspect of the units, understanding the functions, about their derivatives, and also we are going to explore optimization problems. And here I will be breaking down the complex concept into the manageable parts, and also we will work through some essential examples. So if you are looking for just a review or if you are preparing for a test, this will be the best video for you. Let's get into this unit. So first is using the mean value theorem. So what is mean value theorem? The statement is this. If a function f of x is continuous on a closed interval and it should be differentiable on the open interval, then the mean value theorem says that if your function satisfies these two, then there exists at least one point C in the closed open interval a comma b such that, this is the important part, f dash of c equal to f of b minus f of a by b minus a. So what this final output actually is, this is nothing but instantaneous change. This is your instantaneous change and this is average rate of change. So if your function satisfies this condition, there exists at least. So mean value theorem guarantees you at least one point C such that the instantaneous rate will be equal to the average rate. Let's see how this will be in graphical form. So this is a part of a function we are taking from for the interval a to b, and it's continuous. Also, it's differentiable over every point, right? Now, we said instantaneous change is equal to average change, right? So average change represent a secant line connecting A and B. So secant line, and there exists at least one point. They are both represent slope of a line, right? So tangent line, you can draw one over here. So they are parallel lines, their slopes will be equal. So that's what the term says, f dash of C equal to f of B minus f of A by b minus a. There exists at least one. It's not every time one, right? So at least one is possible. So 2, 3 also is possible here. This is an example for one, exactly one tangent line here, right? And this is the C, particular C point. Let's see one more graph. So this is a kind of a sinusoidal graph. And here, if you're going to take an interval from 0 to 0 is your A and 10 is your B. Okay. So throughout this interval, your function is continuous. It's differentiable at every point between the open interval AB. Now, so for sure, our mean value theorem will work here. And there exists at least one point C where secant. So this is the secant line. AB, if you connect, that's the secant line. Here, this have some slope, like 0 is a slope, right? So what are the other tangent lines on the graph? There are so many C's here. First C is here. At this point, C1. The secant and the tangent line have the same slope. They are parallel. So one more C over here. This one. Only 2 C's? No. Third C is also here. So it guarantees for at least one, but there is a condition like this is C3. So here we see an example for 3 different C values, right? This is all about the mean value theorem. Now, let's see a problem. The table shows selected values of f. The function is twice differentiable with f double dash of x greater than 0. Which of the following could be f dash of 5? Okay, f dash of 5 is equal to, because f dash of 5, I know the function. If you know the function, you can differentiate and plug it. But here, no function, just table. So let's apply mean value theorem. F dash of 5 is equal to f of 7. 5 is coming between 3 and 7 as per the values that we have, right? Divided by 7 minus 3. So you just plug in the values now and you got 0.9. So it's option C, right? So that's simple. Using tables, we can just deal with mean value theorem. Now, one more function. One more question. Let f be the function with f of 1 as e, f of 4 as 1 over e, and f dash of x is given as x minus 1 sine ex. How many values of x in open interval 1, 4 satisfies the conclusion of MVT? On the closed interval 1, 4. It's none, 1, 2, more than 2. Right. So, okay. So what does mean value theorems conclude? It concludes like f dash of a particular point is equal to the average between the interval that we are working. So let's find the average because I know the open interval that we are working. F of 1 by 4, average rate of change is f of 4 minus f of 1 by 4 minus 1. And those values are directly over there. You just plug in, right? That's it. Now, f dash of how many points? So you don't know how many points, 1 or 2 or 3, right? So you just equate it. F dash of x should be equal to the average. F dash of x is this expression and average rate change, and solve for your x. That's simple. You will get those x values. And this one we can easily do with the help of Desmos here. Let me show it for you. Let me share a different screen. Okay, so how to solve? You just first give the function, right? And right side of the function, you give it as another function and they will meet. We need the interval 1 to 4. So 1 to 4 region you can shape and the intersection of two function, LHS function and RHS function. So we got around 3 points, right? So it's more than 2. We don't want the points here, just we can see. In this case, you will get the conclusion will satisfy. The MVT conclusion will get satisfied for more than 2 points over here. So that's simple it is. Moving to the board, here we see. So the answer is more than 2. So that's simple it is. Now, 5.2, extreme value theorem. And also we will explore global versus local extrema and critical points. So let's see what extreme value theorem is. The EVT states that if a function is continuous on a closed interval, then f of x has both a global maximum and a global minimum on that interval. If your function is just continuous, then it have both global maximum and a global minimum in that particular interval. So global maximum means the largest value that we are working. If you're working on a particular domain, what is the maximum value your f of x can attain? And global minimum, on the entire domain, what is the smallest value of f of x? That's simple. This is global maximum, global minimum, right? And these extrema must occur at critical points. They can occur at critical points or at the endpoints of the interval. You can get global maximum and minimum at endpoints also or critical points. We will learn more on critical points in upcoming minutes. Now, so what is this AVT guarantees? EVT guarantees existence of extrema. It will say, okay, that is an extrema for sure, but it doesn't say where they occur. So if you want to find out those extremas, we need to analyze the critical points and endpoints because those extremas can occur at these instant, either at critical points or at endpoints. So that's the thing you should understand, right? And now, global extrema, also we see local extrema. There is a kind of difference over here. Global extrema, it's sometimes we will call it as absolute extrema. Absolute maximum is largest value for the entire domain or if you're working on a specified interval. And global maximum is the same. The minimum is the same, is the smallest value over its entire domain. Or there's a specified interval you're working. Now, local extrema or relative extrema, we can say, it occurs at a point x is equal to c, where f of c is greater than f of x for all x near c. So if you're working on an interval AB, you will observe some points, point C, nearer to that, we can say neighborhood. If this is your point C, nearer to that, your C will have the lowest or your C will have the highest value. So that thing is called local or relative maximum. We won't consider the entire domain. We will just work on the neighborhood. In that neighborhood, is your C is getting maximum or minimum. That's simple. And the same thing for relative minimum. It occurs at a point x is equal to c. F of c is smaller than the nearer value, neighborhood. We won't consider x. So just if this is your c, you will analyze over here, right? Not entirely. That's the basic difference. Now, the relationship here is Global extremum is also a local extremum. Sometimes it's possible. But the reverse is not necessarily true. If it's a local extremum, it is local extremum only. We can't take a chance that it can be a global extremum. No. So global can be a local, but local cannot be a global. That's simple. Now, global extrema may occur at critical or endpoints. We already see this. Whereas local extrema will only occur at critical points, right? We won't go for the entire domain over here. We are just working on neighborhood. This is like in overall domain that we are working, right? Now, what is critical point? We come across a lot here, right? So critical point is a function will have a critical point. If it occurs at a point, then they will satisfy two conditions. Either one of this. Your f dash of c will be 0 or your f dash of c will be undefined. Right? If you have any chance, then we call it as critical point. Right? So f dash means tangent. Tangent, it will give you the slope function, right? It's a gradient function. So you will have either horizontal tangent or a vertical tangent. So then that point is a critical point graphically, right? So if you have this is a horizontal tangent. So this is a critical point. If you have something like this, that is a horizontal tangent. This is a critical point, right? And that's simple. And undefined also, if your slope is undefined, then also it's a critical point. Now, how they relate to extrema, critical points and extrema. We seen that, right? Global extrema may occur at critical points, also at endpoints. And local extrema only to critical points. Let's see. Critical points are candidates for local or global extrema. So, but not every critical point is an extrema, right? Not every point is an extremum, but we can take it as a candidate and we will do some test, right? We have a lot of tests coming up, candidate, first derivative, second derivative, to classify the critical points, whether they are local extreme or global extreme, right? So they are very important thing to determine whether a critical point is local maximum, minimum, or sometimes neither. They cannot be neither of those. Now let's see. Use the first derivative test or second derivative test, and candidate test also is there. We will do it only for global things, right? So we will learn about these tests, and this is how the critical points are related. So after this, we will use the critical points a lot, right? So critical point is very simple. If you have a horizontal tangent or a vertical tangent, that point is classified as critical point. Algebraically, f dash of x is 0. For what values of x it becomes 0? Those are your critical points. That's simple, or undefined also. Now, end behavior. For open intervals or unbounded domains, critical points alone are not enough to determine global extrema. The behavior at infinity or asymptotes must also be considered, right? If you are working on an unbounded domains or an open interval, we have to check the end behavior at infinity, or if you see any asymptotes, that also we should consider for global extrema, right? End behavior is also important. Now, how to identify extrema on a closed interval? So if it's a closed interval, solve for f dash of x equals 0, because this will give you critical points. Or f dash of x is undefined, also you have to check. So two things will give you the critical points. Next, evaluate the function. Compute f of x at all critical and endpoints. Endpoints is very clear from the interval. And critical points, you got it over here, and compute the values of f of x. Then compare the values, which is bigger, which is smaller. So the largest value is the global maximum and the smallest is the global minimum, right? So this is kind of global extremas in a closed interval. Now, find all the extremas. Here a graph is given and the red crosses are critical points. And we know that there is two kind of extremas, local and global, like we can say relative or absolute also. Now, first one is, let's go with global. Global minimum is at minus 2, 3. So overall, this is the graph. You're working for this to this, right? In this overall, if you draw this a vertical line, what is the lowest point that can match your graph? This point, right? In the overall domain, it's minus 2, comma 3. And what is the highest point it can match? So global maximum, overall interval you're working. So that is 4, comma something 28, right? It's positive 4, comma 28, right? And coming to relative, relative means I won't consider, I will work on every part of it. Okay, here I see a critical point. So let me just erase this. Right? So for local extrema, for local minimum or local maximum. So if you consider this, around this point, this critical points have the lowest. If you just check the neighborhood, right? And around this neighborhood, you just click on the critical points and check, right? So that is the thing. That is how this will work. So here local minimum is minus 2, comma 3. Around this point, yeah, this critical point, this is the lowest. And 2, comma 0. When you see here, can I say around this point, this is the bigger or this is the smaller? No. So we can't make anything. So it is equal to these values in neighborhood. It is higher. So you can't say that this is the highest or lowest. So no. And 2, comma 0, this is the highest. So maximum. We are working for minimum. And you come here around this. This is the lowest. Around this thing, if you work, this 2, comma 0 is the lowest. So that is how it is. And local maximum, let me erase this. This one, minus 1, comma 3. So around this point, if you check, okay, this is, and this point, actually minus 1, comma 3 won't come. Around this point, these are some greatest values over here. So it's not local maximum, let's ignore it. And 0, comma 4, yes. Around this point, if you check, this have the maximum. It increase, it reaches this and it drops. 0, comma 4. And this also will be neither. So this and this or neither cases. Right? And next thing, determining intervals on which a function is increasing or decreasing. Okay, so we know the critical points, we know how to locate it. And critical points, again, a useful thing over here. Okay, let's see here. This is a function where it is increasing, where it is decreasing. Increasing means left to right, you have to check. It should be increasing. It should be grading up. And left to right, if your function is going down, it's decreasing. That's simple. So here we can easily see that from this point, like minus infinity to this, if we can take this to this, it's increasing. And then it's dropped down, decreasing, increasing, decreasing. So that's simple it is. If I ask you from the behavior from 3 to 4, so this is like 3.5, let it be, right? So 3 to this 3.25, if I take, it's decreasing. And then it start increasing till I can say 3.75, right? And then again, it's dropping down, 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 till 4, it's getting down. It's very simple. Now, every time, graphically, it's so simple, right? But analytically, how to do this? Let's see. So step 1, you have to find f dash of x. Again, f dash of x plays an important role in finding critical points, extremum, and also in the increasing, decreasing behavior. Then set f dash of x is equal to 0. When you equate this, you got your critical point. And after finding critical point, find where the derivatives does not exist. Actually, if your derivative does not exist, we have to include that also in our critical point. So use a sign chart to test intervals. Okay, we will see this in our examples, how to draw the sign chart, right? And the sign chart will say, like after grouping that, for example, 4 and 5, so positive, negative, and positive, this will say where it is positive, where your f of x is negative, where your f dash of x is positive. And with this, we can come to the conclusion. So next is, if you have a positive sign in your sign chart, the function is increasing on that interval. If you have a negative f dash of x, the function is decreasing on that interval. That's simple. Very simple. You find the critical points. All this says critical points. Draw sign chart and give your interpretation. Let's see an example. Suppose the speed of a car S of t in meter per second at time t second is given by the function, right? So we need to find where the speed is given, right? So we are going to analyze where the function is speeding up and where it is speeding down, slowing down, right? So up means increasing. So we are going to analyze the increasing and decreasing behavior here. Okay, so this is missing. You can write it. Analyze increasing, decreasing behavior. Increasing, since the function is speed, increasing means where it's speeding up. Since it's speed, if it's decreasing means actually the interpretation is going to be the where it's slowing down. That's simple. And it's very simple. Find critical points, draw the sign chart, and you have to just go for the interpretation. So solution. Here there is, okay, if just you find S dash of t, S of t is this, and you derivate this, right? It's simple derivative. I'm not explaining here more. And equate to 0, you got only one critical point, which is 3, right? So sign chart is simple. If you have one critical points, your graph has two portions. And how to draw the sign chart? You draw a horizontal line and mark all your critical points. Here I got just one, so it's which is 3, right? And now your aim is this side, is it positive or negative? This side, is it positive or negative? Now how to do that? You have to plug in some values and check for it, right? After 3, you take some 4 and plug in your, this sign chart we are doing for S dash of t, not S of t, right? This, so we have to plug in this function. So I will say S dash of 4, you just have to take a value after 4. You can even take 3.1 also. That's not a problem. So S dash of 4, if you plug in, it is -8 plus 6, which is -2, which is a negative. We just want the sign, not the value. So it's a negative. And this side, to the left of 3, you say take some 0, right? 0 is easy. It's positive. So when you plug in, S dash of 0 is my choice, and you will get a +6. So it's a plus. That's simple. So you can consider this as negative infinity, this as positive infinity. And coming to the conclusion, from -infinity to 3, in this interval, the graph will be increasing. Positive, the interpretation should be increasing. And 3 to positive infinity, it's decreasing. That's all. So we got this, and the interpretation is this. That's simple. And I'm making sure there is an open interval over here. Right. That's simple. 5.3 is. Now 5.4, using the first derivative test to determine relative extrema. Only relative, graphically we know, right? We will look over that particular neighborhood, and if it's that is a minimum or maximum, we will classify that as extrema, local extrema. But what if the function form is given here? Let's see. The algorithm is, again, we depend on critical points. So find f dash of x, find critical points, draw the sign chart. Till this we know already. In increasing, decreasing behavior, we did this. Then conclusion is analyze behavior near critical point. Okay, what should I do? If there is a sign change from minus to plus, this is your critical point. Here it's minus, here it's positive. If it's minus means it's decreasing, and plus means it's increasing. So around this point, this is kind of minimum. Can you see? Right. If it's a positive to minus, increasing to decreasing, this is the peak point, which is a maximum. Right? What if I have minus, no sign change, minus to minus, plus to minus? This case can also occur. This is neither minimum nor maximum. We have this critical point is not a local extremum, but we have other words. We will learn that. Okay. That's simple. 5.4 is, and here we got an example. Let's analyze the behavior, and find whether what are the local extremas over here. So solution, finding critical points and drawing sign chart. Let's quickly do it. F of x, f dash of x equal to 0, solve for it. Your critical points are ready. Now coming to the sign chart. Draw the horizontal line, mark your critical points 0 and 2 and make sure you're writing it in order. Then plug in values. After 2, you can plug in 3 and it's sign chart of f dash of x, not f of x, right? If you plug in, you will get a positive answer. So plus. And here there is, if your sign chart is for a quadratic, it will be alternative in sign, plus minus plus. If you got this, then you just skip the signs. That's simple. Okay, quadratic and your x square coefficient to be positive. Okay, then it's plus minus plus. And we did a sign chart. Now positive to negative, increasing to decreasing, this is maximum. Decreasing to increasing, it's a minimum. That's it. We find the local extremas. That's simple, right? So local maximum at x is 0 and local minimum at x is equal to 2. If you want the coordinates, you just plug in x is equal to 0 in your original function, right? So 0 comma f of 0. This is 2 comma f of 2. Sometimes they will ask for coordinates. And that is quite simple substitution in original function, right? Now 5.5, using the candidates test to determine absolute extrema or global extrema. Okay, for global extrema, what we have? We have candidates test. Let's do that. The candidates test involves evaluating the function. It's simply evaluating. We are not going to differentiate anything over here. You are evaluating the function for the candidate test at the critical points. Okay, where should I test? At critical points, at endpoints of the closed interval. And you have to analyze. If you got a largest function value, it's absolute maximum. If you got a smallest function value, it's absolute minimum. So this is the method we will be using for global extreme values of the function on a specific interval. Let's do this. Find the absolute extrema of this function on this interval. So first, critical points is important. So f dash of x equal to 0 and solve for it. You got your critical points, right? Then critical points and endpoints. These are endpoints. You got critical points. Now you have to compute the values, right? So let's compute f of 0. Endpoints, we are going in order. 5. F of 1, you plug in, you got 9. F of 3 is 5. F of 4 is 9 again. Okay. So compare the values, which is the maximum here. 9 is the maximum, but it occurs at both places. Yes, both are considered as absolute extrema. The absolute extrema occurs at 2 places, at 1, also at 4, and the absolute value is, the absolute maximum value is 9. And also, the absolute minimum occurs at 2.0 and 3. So this is what? Absolute maximum, 2 points, absolute minimum also 2 points, right? It's not like a single point, unique point over here. You can get 2 points also. Right. Now, 5.6, determining concavity of functions over the domain. So far we did first derivative, right? For we either to find critical points and increasing, decreasing behavior, and to find local extrema, global extrema. Everywhere we just use f dash of x, the first derivative. Now in 5.6, we will do the second derivative, the application of second derivative, concavity of a function. If I draw some function like this, it's concave down from here to here, it's concave up from here to here. And graphically, it's quite easy. If it's kind of a inverted U, upward U, like if it's facing up, concave up, facing down, concave down, right? And concavity means where the function describes where the curve bends, in which direction, like upwards or downwards. Second derivatives will tell us about the concavity. So what is the conclusion, how we should make? If your f dash of x is greater than 0, it's over an interval. It's not about a particular point. Over an interval, if you got a positive and the graph is kind of a U there, kind of an upward U. If it's less than 0, it's concave down, something like this. It's not exactly, even this is concave down. Even this is concave down, and this also. right? So algorithm is simple. Find f dash and f double dash and find critical points for f double dash of x, right? Like what will you do? F double dash of x equals 0. Draw the sign chart. And conclusion, if you see positive, concave up, negative, concave down. And that simple it is. So sign change around a critical point, minus to plus or plus to minus. It is a point of inflection. When you see a sign change around a particular point, that is considered as a point of inflection, right? And that's simple. Given f of x is x power 4 minus 4x cubed plus 10x minus 5. Determine the intervals where f of x is concave up or concave down. Identify all points of inflection, including their coordinates. Okay, so for concave up or down, we should find the second derivative and draw the sign chart. F of x, f dash, you know how to find double derivative and equate to 0. So actually the points are x is 0 and x is 2. And draw horizontal line, mark those 2 points, 0 and 2. So after 2, just plug in the value in f double dash. If you plug in 3, it's a positive. So positive, and it's a quadratic, right? So switch the sign, negative, alternate sign, positive. And minus infinity to 0, it's positive. Also 2 to infinity, it's positive. So positive in these intervals, we got concave up. And 0 to 2, it's concave down. Right? And when you're writing the intervals, make sure you're unioning, you're making them join together using union. And concave down at 0, 2. That's simple. And D. Identify all points of inflection, including their coordinates. Okay, point of inflection if there is a sign change. We have a sign chart already. If there is a sign change, then those point are point of inflection. So yeah, here there is a sign change. Actually, it's f double dash, right? Sign change, so it's a point of inflection. 0, we know how I got minus 5. You just plug in the original function. When you're finding coordinate, it's f of x, not any other stuff. And 2, you plug in over there, you got a minus 1. So these are the points of inflection, right? And 7th subunit, using the second derivative test to determine extrema. Actually, to determine extrema, we use first derivative test, right? Let me recall it to you. You will draw the sign chart of f dash of x. And if you've got something like this, negative to positive, it's minimum, positive to negative, it's a maximum. Now, how can we do with second derivative? This is also, it's a method to classify critical points as a local maxima or a local minima based on the concavity, right? So second derivative test, find critical points and compute f double dash of x at each critical point. And your f double dash of c is greater than 0, it's concave up. At that particular point, if you have this kind of shape, right, it's concave up, and up means it's a local minimum, right? Up, minimum. Okay, don't get confused. And f double dash of c is greater than 0, actually is less than 0, concave down at that point, and it's considered as local maximum, right? What if I got equal to 0? The test is inconclusive over there. Then you have to go back to first derivative test. Got it? Let's do a simple thing. An f of x is given. Especially have to apply second derivative test to classify the critical points as local maxima, minima, or other inconclusive. So find f of x, f dash of x. So to get critical points, f dash of x is equal to 0. And we got that. Go for the sign chart. Yeah, f double dash. Second derivative, find f double dash. Then you draw the sign chart. Right? So it's 6 here. Okay, sorry. 2 is a critical point for f double dash of x. For the sign chart, I'm telling. So 2. And after 2, it's going to be positive and negative. Right? So let's work for, now you have to apply the critical points, not this point. Okay, so apply 1. It's going to be less than 0. which is negative, so it's a minimum. And f double dash of 3, it's going to be local maximum over there. Even you can go with sign chart and okay, 3 is over here positive, 1 is over here, it's a negative. That way also we can classify. If you don't want to plug in, if you're well versed with sign chart, you can directly use those two, right? And there is no inconclusive points here. Both critical points are either local minimum or local maximum. Now we have learned a lot. Let's take a quick takeaways over here. Mean value theorem, this will guarantee at least a point where the instantaneous rate equal average rate. And then we did extreme value theorem also. That will give you the extreme values. And extrema and critical points relation is critical points help locate local or global extrema. And extrema occur at critical points or at endpoints. That is global extremes. Increasing, decreasing intervals, for that we have to use f dash of x, and we will determine whether the function rises or falls. So from here, sign chart will work. Increasing, decreasing, f dash sign chart. First derivative is identify local extrema based on the sign changes, right? So positive to negative, negative to positive. This we did, maximum, minimum. Candidate test is to come. In this, we will take the candidates and we will plug in to find global extremas, right? Or who are the candidates? Critical points and endpoints. And concavity, it depends on second derivative. F double dash of x reveals whether the function is concave up. If you got a positive value over an interval, over that interval, it's concave up. If you got a negative, it's down. Here we will use sign chart for f double dash. And second derivative test, again to find the extremas, right? Local extremas. And here we will use, we will find critical points, and then we will find f double dash of x. Then we will plug in those critical points. If you got positive, it is, okay. So if you got a positive thing, it's a maxima. And if it's a negative thing, it's a minima. Right? Now 5.8, sketching graphs of functions and their derivatives. This is very important. So pay attention. Given f of x, sketch f dash of x. So this is my f of x. This is a sketch of the f dash of x. How we will be doing that? We know some behavior, right? So look for horizontal and vertical tangent first of all. Your f of x have a horizontal tangent, right? Okay. Horizontal tangent means f dash of x is equal to 0. So at this point, if this point is A, at that point on f dash of x will be x-intercept. If you have a horizontal tangent here, that is x-intercept in f dash of x. This implies f dash of x is 0. So you just replicate the same, right? And this is your f of x. Your f of x is concave down, but it's f dash of x, right? Okay. So around this point, you can see something over here. Like this is your C1. This is your, okay, let it be C, just C, okay? So after this point, it's kind of increasing mode. Again, it's increasing. So it's a kind of negative over that point. So from this to this, it's negative. So negative means below x-axis. So around that C, actually we need to make something like this. Okay, so this have to be over here. So this is having negative. So your f of x is negative means your f dash of x, it replicates something like this. And if it's increasing mode like this, it is the graph at f dash of x will be above x-axis and increasing, right? Now this is your f of x, and it have f of x is 0, okay, and this has a horizontal tangent here. So at this point A, the graph will cross the x-axis. So from this to this till A, it's decreasing. So your f of x is decreasing, your f dash of x should be negative. Negative means below x-axis. Your f of x is positive means it should go above x-axis. That's simple. And this is your f of x, your f dash of x is something like this. Okay, what can I do? It crosses x-axis at this point. And it's throughout, it's kind of increasing only, right? So if it's a linear function, if it's just kind of y is equal to 2x plus 5, you will get just 2. So it will be a constant. Like it's a line, so the tangent, wherever you calculate the slope, it will be the same, right? So it's a constant after differentiating. It's a constant function. Now, we have to memorize this, or you can use this trick to sketch. So critical point, increasing, decreasing, inflection point, concave up, concave down for f of x. Like f dash of x also will have the same thing, f double dash. So critical point in your f of x means f dash of x will be 0. Increasing, if your f of x is increasing, then your f dash of x is positive. Positive means above x-axis, right? 0 means intercept, x-intercept. And negative means below x-axis. That's the thing. So we have to sketch in that way. And inflection point, it should be a critical point in f of x. If your graph is concave up, your f dash of x will be increasing. If your graph has concave down, your f dash of x will be decreasing. And the same thing, you just write inflection concave up and you just copy paste the same, right? So this is an important thing for any function. If you know this, you can easily sketch this. Now, connecting a function, its derivative and its second derivative. You can use the same trick over here. Let me give an example. This is your f dash. You have to find f of x. Let's do how to sketch. It's just a sketch, not an exact graph. And let's do. Right. So here, f dash of x means f dash of x is equal to 0 at these points. X is 1, 3, and 5, which means it have a horizontal tangent. Your f of x have horizontal tangents over here. So horizontal tangents, let me check. I don't know where the horizontal tangent will come. I'm just checking some random point here. So your f of x here, maybe here. I'm just making like this. It cannot be like same, but yeah. This is the first thing. Look for the 0 or undefined points. Now, to the left of 1, what happens? It's negative. Your f dash of x is negative means your f of x is, let me show you. F dash of x negative, which means f of x is decreasing, right? So it's decreasing. Your function should be decreasing, something like this, dropping down. So I know one party over here. Okay, it's coming like this. It's not going like this, right? So we decide that. Then after that, I think it will move up, but let's check. 1 to 3. What happens? It's completely above x-axis. Above x-axis means positive. Positive means decreasing. F dash is positive. F is increasing. So increasing means this is the lowest point and it will increase, right? And at 4, what happens? Okay, at 3, what happens? At 3, again a horizontal tangent. So it should be increasing, and it should, at 3, again, the thing should become horizontal. So your f dash of x is positive from 1 to 3, right? Okay, now how should I make the tangent? Because 1 to 3, it's increasing. So I should do something. I should change the place over here, right? So you change, and the 3 will be somewhere over here. So now it will make a sense, right? So 1 to 3, your f is increasing, and at 3, you got a horizontal tangent. Then it's again 3 to 5, it's go below x-axis. And at 5, it make a horizontal tangent. It's something like this. Okay. So not a neat sketch, but I hope you understand. This is f dash. From f dash, we draw f of x. Make sure you are using the table side by side. Once you practice a lot, you will make that in a minute, I will say. That simple it is. Now, given f of x, sketch f dash of x. Okay, f of x is given and look for horizontal tangents. Okay, f of x have horizontal tangent means at those points, f dash will cross 0. Horizontal tangents, f dash x equals 0. So at 1, you need to cross. At 3, you need to cross. At 5 also, you need to cross. Now, and your f dash of x, it's completely above x-axis. F dash x means this is decreasing and then increasing, then decreasing and increasing. So f dash of x going down means, oh, f of x is going down. F of x is going down means f dash of x should be negative. So going down, you should go down below the x-axis. And if it's increasing from 1 to 3, 1 to 3, you should go upwards. But I can't go like this, right? Because I need to come back over here. So just make something. I have made here, you can make over here also. That won't be a problem. It's just a normal sketch. Right? And let's do this. So here to here. Then this to this, it's decreasing. I will go like this here. And then after 5, it's increasing. So you go above x-axis. Right? So that's the basic idea of sketching. Now, introduction to optimization problems. The very important application. We understand the behavior so far, and most of the techniques we will be using here also for optimization problem. Write equation in one variable. Actually, a real life scenario will be given. You have to make your equation in one variable. That is your objective function, we will say. Right? Differentiate, find critical points. You can use first derivative or second derivative to find relative extremas. Actually, our main function is we will get a function. Either I have to maximize or minimize the stuff, and you need to interpret the result. Right? So a farmer wants to build a rectangular fence using 100 meter of fencing material. One side of the rectangle is along a river and doesn't need fencing. What dimensions maximize the area of rectangle? Okay, we have a rectangle. You have 100 meter of fencing material. One side is along the river. That doesn't need fencing. Okay, now I need to maximize the area. If there is a river, perimeter will not get affected, but area is complete thing. Area is still L into B. So now our aim is to, and we understand the situation, make a clean diagram that will help you in better visualization. And now, let my length be L and breadth be B, and perimeter is, actually I have to make in single variable, right? So I have two variable. Let's try to make into single variable. L plus 2B is 100. Okay, so it's not 2L plus 2B, make sure, right? And L is 100 minus 2B. So in terms of L, I can use 100 minus 2B. So now it's a single variable. What is an objective function? Area. Area is L into B. I know L is 100 minus B and, 100 minus 2B into B. That's simple. This is what the introduction. Then what dimensions will maximize? To find the solution, that is covered in the next subunit, which is solving optimization problem. But this is all the things you should make sure from the given question. You have to understand, make a diagram and make your objective function. Now, solving this, you can apply first derivative or second derivative test, right? Here I need to maximize. So we have all those things already did. Here, this is our area, and make sure you're making into the standard form. And I'm finding dA by dB, differentiating area with respect to breadth. Find critical points, and you got only one critical points. Okay, what is our aim? Maximize. So you have to find the local maxima. Okay, whatever the methods you know, you can use it. Determine extrema. So You can apply second derivative as it's simple function, right? Second derivative will quickly help us. D square A by dB square is minus 4. So throughout the function, it's kind of concave downwards, right? Negative means. So d square A by dB square is always negative. So second derivative test says that particular, where whatever point you're looking for, not only at 25. So whatever point, you will have a maximum. So b equal to 25 is the maximum point, right? And what if you want to do the first derivative test? This is a first derivative and 25 is a critical point. You will check positive and negative t. After 25, if you plug in some values, you will get a negative. And here it's a positive. So positive to negative, it's a maximum. So 25 is maximum. Here I got 1 point, and that 1 point is also, using the test, I proved it's a maximum point. So when your breadth is 25, your area will get maximized. Now let's interpret the result. We got B is 25. Let's calculate L also. So the to maximize area, the dimensions have to be 25 by 50 meters. Right? And what is the maximum area? Just plug in and find it. That's simple. Now 5.12, exploring behaviors of implicit relations. Okay. So we learned a lot. We are going to explore all those with the implicit relation. First thing, here an implicit equation and it's simple given. Use implicit differentiation to find dy by dx, find critical points, use SDT to determine the concavity and classify them. It's same, whatever we did, the concept is same, but only implicit form. First one, write the function implicit differentiation 2x plus 2y dy by dx. Chain rule, right? And dy by dx is minus x by y. That's simple. Next, to find critical points, you have to equate dy by dx equals 0. So you have to make sure, work for horizontal, also vertical tangent. Horizontal tangent means numerator is 0, so x is 0. When x is 0, y is plus or minus root 5. You have to plug in over here. So the critical points are 0, root 5, 0, minus 5. Not only this, vertical tangents also will be classified as critical points. So dy by dx is 1 over 0. Right? It can be 1 or any number by 0. So if your y is 0, then there is a chance it's a vertical tangents and vertical tangents at these points. So these are your critical points. Right? Now, solution for C, we have to use second derivative test to test the concavity. We got dy by dx. Now we have to find d square y by dx square. Very simple. Again, implicit form like u by v. So minus u dash, you can just keep as it is. And then v as it is. Then v dash u by v square, right? You just apply this. And you got something like this. D square y by dx square is minus x squared by y minus y by y square. Right? And compute the values. We have to check where it's positive. We already got a critical points, right? So at 0 comma root 5, you got less than 0. So 0 root 5 is local maximum. And this cases, it's greater than 0, so it's local minimum. I didn't use the vertical tangents over here, right? So that's all. We covered all the subunits. I hope this video might be helpful for you. That's the wrap for this video. I will be meeting you with yet another interesting one-shot review for AP Calculus AB as well as BC. Until then, keep learning and keep practicing. And also, if you like this and if this really helps you, you can share, you can like it, subscribe, and you can support us. Thank you so much for watching.